So we showed with the anode polarization data for chlorine gas production, we got current density or potential. We calculated the natural log of current density, and we used linear fitting between natural log of current density and our potential to get the fitted slope B and the fitted intercept A. And then with the equations for TOEFL slope and the intercept, we can calculate the 1 minus beta, 1 minus temperature factor, as well as the exchange current density J0. That was what we showed in previous slide. But we said, okay, these two parameters, 1 minus beta and the exchange current density, can also be obtained by fitting current density and our potential, but directly to the BV or Butler-Volmer equation. And then let's do this: direct fitting of current density and our potential, the entire data into Butler-Volmer equation. And then we can also get 1 minus beta and so on J0. And that's what we are going to look at here and compare with what we got from TOEFL. Again, remember for TOEFL, we should only use the data for our potential that is significant. In this case, we use the data greater than 0.05 volt or greater than 50 millivolt from this line and above. Okay? So with the current density and our potential, now let's look at how are we going to get the 1 minus beta and J0 value by fitting directly to Butler-Volmer equation, which in fact we have done before. So this shows the initial J you can calculate from Butler-Volmer equation using the over potential. So this column, this uncolored J column, would be the measured current density, but with the over potential value, as well as if we put some initial gas, value for 1 minus beta and 1 as J0. So if we guess 1 minus beta to be 0.5, we put it here, and the J0 exchange current density, if our initial gas is 1 amp per meter square, we use these two values, and with the Butler-Volmer equation, we can calculate current density for corresponding our potential. Okay? And the values are listed here. So the data here are calculated from our potential value measured here using the initial gas value for 1 minus beta, which is 0.5, and exchange current density data, which we guessed as 1 amp per meter square. Using this gas value and our potential, we calculate current density. So this is measured current density. This column gives the calculated current density directly from Butler-Volmer equation using the initial gas value. And then we can calculate the so-called error. The error or the difference between experimental measured value and the calculated from Butler-Volmer equation. Essentially, J measured value column here minus J from Butler-Volmer equation column here. And we can calculate the difference. For example, if the calculated value is 0.4 while the measured value is 30, then the error would be approximately 30 amp per meter square. Okay, so this column is calculated as a difference between measured value and the calculated value. The calculated value is from the Butler-Volmer equation with the parameters, the 1 minus beta and the J0 parameter initially guessed at 0.5 and 1 amp per meter square. Okay. Then, with all the error value for different overpotentials, we can also calculate sum of error squared. Or in Excel, there's a function called sum square, which means for each of these error, it would do the square term and then sum it up, add them up together. And the sum of error squared value for all these errors are stored in this cell. And for this initial case, it comes to be a very big number, 5 times 5.39 times 10 to the power of 9, a very large number for the sum square value. Okay, so this is initial gas, and we can calculate J for BV, and we can calculate error for the calculated value versus the experimental value, and then for all those error we can do a sum square of all the error, and it came to be a big number. Then, as we said earlier, we can use the solver function, the solver capability within Excel, the solver capability or add-on within Excel. Okay, using Excel solver as what we have demonstrated before to provide better fitted value for 1 minus beta. In this case, would be the cell E27. E27, that will be the value for 1 minus beta evaluated from Butler-Volmer equation. And similarly, the J0 exchange current density value would be in E28. That will be the exchange current density. And here in this figure, I'm still showing the initial gas value 0.5 for 1 minus beta and 1 amp meter square for the initially gassed J0 value. Okay, and we can use Excel solver. If you press Excel solver, we get a dialog box, something like this. We get a dialog box solver parameters if you press Excel solver. And then the first thing is to set objective, which means what is the objective? Where are we going? So our objective when we do this fitting, as we explained earlier, would be for the sum of error squared for this term, which we call cell F29, F29 for cell F29, which is the sum of error squared for all these error values you square and added them up. For this term F29 to be minimized, to reach minimum. So that would be the overall objective. When we do this fitting, we try to make this cell, which is the sum of error squared, to be minimum. So whatever we do to the parameter, we have to try to make this to be smallest. That will be the objective. And then the second part is to determine what would be the parameters that the Excel solver would optimize or fit to give us to reach the objective. So this here, by changing variable cells, we have two cells. One is cell E27, this one for 1 minus beta. The other one would be for cell E28 for J0. So these two cells would be the parameters to be fitted, or we change the Excel software would change systematically the values for these two cells in order to reach the objective, which is to minimize the sum of error squared, minimize this value, the cell 29 value, to minimize it by changing these two cells. Okay. Then of course, when we think of fitting, we would have sometimes constraints subject to the constraint. Here we only have one constraint for 1 minus beta, 1 minus the symmetry factor, which is the cell E27. Cell E27, it has to be smaller than 1 because we said um, symmetry factor in this case should typically between 0 to 1. Let's say the value is smaller than 1. And then this one tells for the fitting, we want all the parameter to be non-negative. Okay. And then you click solve. The Excel solver would do the computation and try to fit the data to find the optimized 1 minus beta, which is cell E27, and J0, which is cell E28, in order to reach the objective, which is to minimize the value of cell F29, the sum of squared to reach minimum. Okay, and then if you click the solve, okay, Excel solver would provide fitted 1 minus beta, the symmetry factor 1 minus symmetry factor, and J0 exchange current density value that actually minimizes the sum of error squared, which is our cell F29. Cell F29. So if it does the job, then if it's successful, we will come up with this dialog box. And here it says solver has converged to the current solution, which means the Excel solver found an optimized solution that converge and with all the constraints, all the conditions are satisfied. For example, we said the 1 minus beta has to be smaller than 1. Okay, so these are the numbers that we got: 0.336 for 1 minus beta, and then 225 amps per meter square for the fitted J0 value. So these are the fitted values for 1 minus beta and J0 by using Excel solver to fit directly into Butler-Volmer equation for current density and overpotential. So these values are obtained by fitting the data, trying to find optimized 1 minus beta and J0 value so that all the error between experiment and calculated from Butler-Volmer. Experiment is in column A, while calculated directly current value are in column E. And the difference between these, you do the error and then do the sum of error squared gives you this value. But the solver gives us the optimized value for parameters 1 minus beta and J0 that minimize. Remember previously this number was on the order 10 to the power of 9. Now it got greatly reduced to the power of 2.13 to the power of 3. Okay, so now we reach the solution and we have fitted values for 1 minus beta as well as fitted value for J0. And you would pay attention, if you pay attention, you would see that the fitted value by TOEFL 0.317 and 291 is somewhat different from the value fitted directly from Butler-Volmer equation 0.336 and 295. But to us, this is reasonably close. Quite often for electrochemistry, we only request the value to be on the same order, and for this, it is the result satisfies. 0.317, 0.336. The difference is less than 10%. 291 versus 225. It's slightly relatively larger difference, but still between 200 to 300. So you see they are on the same order. The values you get from TOEFL versus you get from Butler-Bowman, they should be close but not be exact. But they are on the same order.